Good morning, I'm Derek Adams, and I'll be presenting on neural additive networks for inferential sensor design. The scope of my presentation is going to be the background of inferential sensor and then some existing approaches to designing those sensors, and then what I propose in this research and other comparative studies that I did, and finally I will present the summary of what we did. In a typical chemical process, you have quality variables that are essential to making critical decisions for the plant's operations. So you look at an example of a Tennessee-Eastman process where you have a chemical reactor with reaction taking place in it. You produce those reactants which goes into those products that goes into the condenser, and then the gaseous products are being sent to the separator where you take out the gaseous product into a stripper, and then finally you get the product that is being designed to the next stage. But most of the cases you realize that there are points in the streams that you need those variables to be able to decide what to do or how to optimize the process. And in such case we have places like the stream 6, 9 and 11. These are very critical to deciding how to operate the plant optimally. And most of the time you have other sensors or hard sensors that are used to measure those variables. But most of the cases these sensors they take a longer time to get the quality variables. And at the same time, because of this hurdle, it becomes difficult to do online optimization, and also it results in you producing off-specified products. And there are cases where you have a company recording a product that has been sent to outside and also reworking on those things. That leads to costs to the company. And in case of hardware sensors, we have downtimes that have to maintain those equipment. All these hamper the development or the process of getting optimal operating conditions. So to be able to achieve that, we propose a neural additive network for sensor design. Most of the existing approaches that we have in the literature, the go-to option mostly is mathematical models, where you have to understand the physical behavior of the system. And in such cases, you have issues like you having to understand the process from ground to know the physics behind it and able to understand from inside out the chemistry behind all those processes. Most of the cases, these are very complex to come by in situations where the process itself is very complicated to understand. So it also takes a longer time to be able to develop all these models. So people now, in this case, move to data-driven models, where we call it black box models. And in these black box models, you have mostly linear models or nonlinear models. And as we all know, black box models that are data-driven, they are hungry for data to be able to produce very accurate predictions. Most of the cases for linear models, they don't perform well on highly complex systems. And so you resort to nonlinear models. And for nonlinear models, they are so complex such that you cannot really understand how the model is behaving. You can't generate any intelligible parameters to be able to evaluate how well the model is predicting the target variables that you're interested in. And also because they are black box, we sometimes are very hesitant to trust how accurate the model is, because we don't have any idea as to whether the model is behaving correctly or wrongly. So this motivated us to develop a neural additive network that we can see inside the model's behavior to be able to know that we can trust this model. Now, how is a fully connected neural network constructed? This conventionally, you have all the inputs being fully connected to the hidden layers and to your outputs. These are so dense such that you can't really understand what the model is actually doing. Although you could argue that the higher or the denser the neural network, the higher the accuracy. That is not proven in any case, that having very complex neural network gives you higher accuracy. You could have simple models that are highly interpretable that can also equally perform well on any task. So in this case, the question is, why not we converting this highly dense neural network into subnetwork that we can interpret or understand how the model is behaving. So this we creating subnetworks that functions more of a neural additive network. So you can see each subnetwork as a parameterized function that are being added together, and we have a bias at the end of it. So each subnetwork is a function that is parameterized. We're able to know which of the components is contributing to the overall prediction of the output. This overall gives you the understanding of how the model is also behaving. So for the example that I showed, we use the Tennessee Eastman process. And looking at the example of stream 9, it is essential to know that you're not having most of your components being patched out. You want all the components to be in the product stream. Most of the target variables to be in the product stream. So these are very essential to decide whether you're running at a loss or the company is making profits in its process. So we did the comparative studies and realized that for the neural additive network we constructed compared to the existing approach of what people normally use, the accuracy for the predictions is almost the same. So for this stream, it has like 4 components in the stream. If you compare the accuracy, they are more like the other complex models that you cannot interpret. But this model that we developed, you can interpret from the model's behavior, not using any other model but the model itself. So if you look at the results, although the accuracy or the error is not that significantly lesser than the others, but it offers other benefits that the others cannot provide us. So that's making it very attractive to focus on it, to know how best you can utilize it in making our predictions better. So when the model is trained, after the training, you could generate an overall overview of how each feature is contributing to the overall prediction of every component that you are targeting. So this insight gives you the knowledge of knowing which features are essential to your model's training, and also it helps you to understand how the model is using the features to be able to predict the target variable that you are interested in. This you cannot get with the other black box models. And also, because you have different models behaving towards different targets, you realize that you'll be able to see how this input varies per every target that you are interested in. So this is very essential in you understanding whether the plant is behaving normally or there is an inconsistency in the whole operation. And lastly, we are able to also detect whether some input features are not essential to the model's training. If you look at the components for 30, you realize that these features are so low compared to the other features. And so if you want to reduce the number of features that you are using for your training, these are things you can look into to remove those features so that your model can train well and get accurate predictions. These you cannot obtain from the other black box models that you have. Also, after the training, we are able to generate the behavior of every input feature towards the target that you are predicting. And these give you the profiles of each behavior as your input ranges increases. So if you look at the stream, there are lots, so I just used a few of them to illustrate my point. We have the stream component 29 and 30. Where they all have different behaviors with respect to the input toward the target. So if in a normal sense, if you're using a deep neural network and you don't understand how the model is behaving, and probably you thought that maybe this feature, if I should increase, when I increase it, it doesn't have any impact in the prediction of the output. You might be tempted to say that this feature is not relevant to the model's learning. But realize that when you increase the values, it increases exponentially. So that gives you an insight that behavior can help you to know how to tune your input to be able to generate a targeted value that you are interested in. So these you can't generate from a fully condensed neural network. Also, you have this plot where you have the deeper regions, the deeper red regions. That one to gives you insight as to the amount of input or the amount of instances that your model received in training. So if you have, let's say, your input followed within the region of deeper stripes, then that gives the insight that you are confident to know that the model had enough data within that region to train on a prediction, so you're confident in your prediction. And if you have other inputs falling outside of that region, that makes you skeptical as to whether the model is going to perform well or not. And also, when you're done with the training, we can do away with the model that you've trained and also use the graphical representation of the model to do the prediction. Then this is very essential to process control engineers to make different cases in their own tests. So for example, in this scenario that we have, I can choose inputs at different input features that I have, and that'll give you the corresponding contributions to the overall target. So when you add all these contributions, that gives you the overall prediction of the model. So for example, if I choose different inputs, in this case, it generates the contribution to the model's prediction. And when you add all these and you add your bias to it, that gives you the prediction of the model. So in you always going back to the model to make predictions, you can do away with the model and use the graph that you generate out of your training to do your predictions. And lastly, in a case where we have different points in the process where there are quality variables that are essential to be determined, you could have this interpretable model to do multitask training. So for all these multitask training, what I mean is that if you want to train, let's say, you want to train to predict any target variable here, the variables here wouldn't be used in your training conventionally. But in deeper other conventional methods, you would have to maybe train one neural network and train different networks for the entire process. But with this, you could have one model where each of them is targeting only the ones that you assign them to, and they will use different features to train, and they will do it in one-time training. So this is very important in cutting down the computational time or wasting a lot of time in training several models to make just a prediction for one process. So these are the benefits that you get from generating an interpretable neural additive network for a sensor design. So after the studies, realized that developing an interpretable model can equally perform well as any complex black box model. And then when you are able to construct these interpretable models, you are able to see which features are irrelevant to your model's training, and that you can do away with any unnecessary features that does nothing to your model's accuracy. And also, after the training, you can also do away with your model so that you can use only a graphic the plots that you generate from your training. And that could be used to make predictions anytime, anywhere. And lastly, the insights that you generate from the model's interpretation can help you to also optimize and control, because you get to understand how the model is behaving. Just as you have any other strategies that exploit the model's way of achieving higher performance, so can you also look at this insight to also increase the model's performance in its accuracy. And lastly, understanding the model's behavior also build confidence in high-stake decisions, because you know that you cannot trust a model that you don't understand. But if you get this understanding, it's always to be confident that this prediction is accurate from this model because you understand it and it correlates with the physics of the process. Thank you so much for your time.
Okay, thank you. So we have time to take one question from audiences. So, any question? I have one question. So you mentioned that in your case, you have 33 input features, right?
Yes, please.
Then how you build your additive neural network model? You build 33 independent models for all the individual features, or because features are not independent, right? So some features can be understood more accurately combination fashion, so right? So can you explain how you build the model quickly?
So most of the cases you have, when you are generating interpretable model, there are instances where you have to generate interactive features. That is, whether the model they are interacting with each other. So they normally add it, or you subtract, or you divide them to give the interactive features. But this model, we have a model of different subnets with neural networks that are like multi-inputs. So that's giving to, so that one split the neural network according to the number of inputs. Then when you train it on each input layer, you combine it at a node. And that node is parameterized, so that gives the interaction between the features. So that interaction that you generate from it is based on these parameters that are assigned to the function of the neural network. So that one weighted to see which one is essential to the model's outcome. So that interactive is based on the relevance of those inputs into its target. So this is where you get the interactions with the features that you train.
Okay, thank you for your answer.
You're welcome.
Okay, so let's thank the speaker again.